This is the second of our videos in Chapter 17. This one is dealing with decibels. Before we get started, let's review a little bit of the math that we might need to use for decibels. We'll recall the following relationships for logarithms, base 10. If you have a log of a product, a times b, that's equal to the log of a plus the log of b. So you just separate the logs. The log of a quotient, a divided by b, is equal to the log of a minus the log of b. And if you have log of a to a power b, you can decrement the power, put it out front, and that's equal to b log a. So this is fun logarithmic math that you may recall from earlier days that you haven't probably used very much. But if you're dealing with decibels, you're going to use it a lot more. Why do we need decibels? Why do we need an intensity level? Well, we saw in the previous little lecture that intensity can vary 12 orders of magnitude. So we can go from the threshold of hearing to the threshold of pain, and that is 12 orders of magnitude, 10 times 10 times 10 times 10 times 10 times 10 times 12 times. And so that, if we try to think of that as a linear range, that would be too much to try to deal with in a linear sense. So we need a level where we can talk about sound, the total possibilities of sound, on a more logical level. So we developed this intensity level. The range of sound intensities discernible by the human ear is very large, so we define here beta as the intensity level, which uses a logarithmic scale. And by definition, then, beta is equal to 10 log intensity over intensity naught. The intensity naught is some reference intensity that we use for all of our measurements. In this case, the units of decibels, or beta is decibels, and our reference intensity I naught is the threshold of hearing, which we introduced before. It has a value of 1 times 10 to the minus 12, or we could just say 10 to the minus 12 watts per meter squared. That is the lowest intensity that a normal human ear can discern, the threshold of hearing, and that is our reference intensity that we use in this formula, 10 to the minus 12 watts per meter squared. So in decibels, the threshold of hearing would be at a value of I naught. Log of I naught over I naught is a log of 1. And what the log is the power that you would raise the 10 to in order to get that value of 1 in this case. So 10 to the 0 power equals 1. So log of 1 is in fact 0. And so the intensity level at the threshold of hearing is indeed 0 decibels. So at 0 decibels, that is the lowest end on the scale of human hearing. And that kind of makes sense. In contrast, the threshold of pain, which corresponds to an intensity of 1 watt per meter squared, has an intensity level of 10 log 1 over 10 to the minus 12, which would be the log of 10 to the 12. And if I took the 12 and decrement that down, I would have 120 times the log of 10, which is 120 decibels. So we're talking about human hearing as a range of dealing between 0 decibels at the threshold of hearing to 120 decibels at the threshold of pain. And that is now a scale that is we're more able to deal with. Here are some sound intensity levels. Rustling leaves is about 10 decibels. A whisper is about 30 decibels. Normal conversation, 50 decibels. A vacuum cleaner, 70 decibels. Every time you go up 10 decibels on the scale is a factor of 10 in intensity. Busy traffic is about 80 decibels. Power mower, 100 decibels. So a power mower is 10 times 10 or 100 times more intense than busy traffic. Siren or rock concert, 120 decibels. So a rock concert is at that threshold of pain. A good name for a rock group or a heavy metal group would be the threshold of pain, 120 decibels. A jackhammer is 130 decibels, and a nearby jet airplane is 150 decibels. So if you were to put your ear to a nearby jet airplane, you would be hearing 30 decibels more than a rock concert, so it would be 10 times 10 times 10, or 1,000 times more intense than the threshold of pain or a rock concert. So don't do as I suggested. Don't put your ear to a nearby jet airplane. It would not be good. Kind of like dipping your head in mercury. Not good. Don't do anything I say at home. Doubling your intensity by 2, or doubling your intensity, results in a change of decibels by 3. Here's a proof. Let's say your decibel level is 10 log intensity over intensity naught, and you doubled your intensity. So now your new intensity is 2I over I naught. Your intensity level, which I'm calling beta prime, is 10 times the log of 2I over I naught. But we know with logarithms we can separate the product. And so now we have 10 log I over I naught plus 10 log 2. This 10 log I over I naught is our original decibel level. And the 10 log 2, if you were to calculate that out on your calculator using log base 10, comes out very, very close to 3.0 something. So we have that our new intensity level is our original intensity level plus 3 decibels. So by increasing by a factor of 2, we increase our decibel level by 3 decibels. If we increase by a factor of 10, that is an increase in decibel level by 10 decibels. And here's the same type of proof. Our original decibel level is 10 log I over I naught, but now we have a new intensity that's 10 times greater. And so our new intensity level, beta prime, is 10 log 10I over I naught. We can separate this with our logarithmic math. And we have 10 log I over I naught plus 10 log 10. This 10 log I over I naught is our original decibel level. And the 10 log 10, log of 10 is 1. 10 times that is 10. So we've increased our decibel level by 10 decibels. So a factor of 10 in intensity is 10 decibels in decibel level. Let's try this out. Calculate the sound level in decibels of a sound wave that has an intensity of 400 microwatts per meter squared. Intensity level is 10 times the log of intensity over intensity naught. In this case, that's going to be 10 log. 400 microwatts is 4 times 10 to the minus 4 watts per meter squared. And our reference intensity is 10 to the minus 12 watts per meter squared. So we have 4 times 10 to the 8, which we could separate as 10 log 4 plus 10 log 10 to the 8, which if we did that on the calculator or did this on the calculator, we would get 86 decibels. Here's a quote-unquote shortcut method. Imagine that the threshold of pain, which corresponds to 1 watt per meter squared of intensity, corresponds to a decibel level of 120 decibels. So we're going to start there at the threshold of pain. If I went up 10 decibels, my intensity would increase by a factor of 10. So for every 10 decibels I go up, it's a factor of 10 in intensity. For every 3 decibels I go up, that's a factor of 2. So, for instance, if I had an intensity of 20 watts per meter squared, that's a factor of 10 times a factor of 2. So my intensity level would be 120 decibels plus 10 decibels plus 3 decibels. So 133 decibels would be an intensity of 20 watts per meter squared. Kind of cool. If I need to go in increments of 1 decibel from that, then that's a factor of 1.26. I can even go down. So for every 10 decibels I go down from 120, that's going to be dividing my intensity by 10. For every 3 decibels I go down, that'll be dividing my intensity by 2. And for every single decibel I go down, that's dividing by 1.26. So we can recreate an intensity that goes with an intensity level. Kind of a shortcut method if you don't want to deal with calculators and you're out in the field, say you're working on radar systems, and you can make a calculation real quick in your head using this so-called shortcut method. Let's see how it might work on this last problem that we did. If we start at the threshold of pain, 120 decibels corresponding to 1 watt per meter squared, and we go down 110 decibels, we go down 10 decibels. Now we have an intensity of 0.1 watt per meter squared. Go down another 10 decibels, now we have an intensity of 0.01. Another 10 decibels, 0.001. Another 10 decibels, 0.0001. So we're down to 1 times 10 to the minus 4 watts per meter squared, or 80 decibels. But we had an intensity of 4 times 10 to the minus 4 watts per meter squared. So we need to multiply this by 2, which will increase our decibel level by 3 decibels. And then we need to multiply it by 2 again. So now we have 0.004, which is 4 times 10 to the minus 4 watts per meter squared. And we've added another 3 decibels to that. So that corresponds to 86 decibels, which is the answer we got on the previous problem. Not really a shortcut method if you have a calculator handy, but just a way to visualize quickly a change of intensity with a change in intensity level. Reversing direction from the definition of intensity level, beta, note that we can get intensity as well. In other words, if I start from the definition of intensity level, multiply or divide both sides by 10, I get this expression. And then to reverse the log base 10 logarithm, I'm going to raise both sides of the equals to the power of 10. That's going to be reverse operations of 10 to the log on the left-hand side, so they cancel out. And then on the right-hand side, I'm going to have 10 to the beta divided by 10. Multiply both sides by I naught, and I have that my intensity is equal to I naught 10 to the beta divided by 10. Since I naught is the threshold of hearing at 10 to the minus 12, I'm going to plug that in and simplify further, and I get this nice expression. My intensity is equal to 10 to my intensity level beta in decibels minus 120 over 10. So if I were given a decibel level in terms of units of decibels, I can convert that easily to intensity in watts per meter squared using this neat little formula here. Now, I'm not sure your book has this formula, so this is a neat little formula just to have handy. Intensity is equal to 10, beta minus 120 divided by 10. Let's try this out with an example problem. A family ice show is held in an enclosed arena. The skaters perform the music with a sound level of 80 decibels. This is too loud for your baby, who consequently yells at a level of 75 decibels. What total sound intensity now engulfs you? So you have this ice show going on, and in the middle of it, your baby is yelling. The ice show is 80 decibels, your baby is 75 decibels, but you can't linearly add decibels. You can't say 80 plus 75 is 155. You can't do that. You can add intensities, so we can convert these decibel levels to intensities, add the intensities together, and then convert back to get intensity level. So we want to figure out what are the respective intensities of the ice skaters and the baby, respectively. So the intensity of the show is 10 to the beta of the show minus 120 over 10. We had 80 decibels, so it's 10 to the 80 minus 120 over 10, or 10 to the minus 4 watts per meter squared. The intensity of the baby, which is my nephew as a matter of fact, is 10 to the decibel level of the baby, 75 decibels minus 120 over 10, or 10 to the minus 4.5 If we do that on the calculator, we can get a scientific result. Or I can do it this way, 10 to the 0.5 times 10 to the minus 5. And the square root of 10, or 10 to the 0.5, is 3.2. So this is 3.2 times 10 to the minus 5 watts per meter squared. I'm going to add these two intensities together. And if I do, the intensity of the show plus the intensity of the baby is 1.32 times 10 minus 4 watts per meter squared. And now I have the total intensity, which is a linear idea, and I'm going to now convert that back to the logarithmic sound level. So my intensity level is 10 log total intensity divided by reference intensity I naught. 10 log 1.32 times 10 minus 4 divided by 10 to the minus 12. And if I do that on the calculator, that'll be 10 times 8 plus the log of 1.32, or 81.2 decibels. So if I had 80 decibels of sound from the show, 75 decibels of sound from the baby, I add them together, and the combined effect is 81.2 decibels. Not a whole lot of change. You can think that if I had 80 decibels from the show, and if my baby were screaming at 80 decibels as well, then the combined effect of 80 decibels plus 80 decibels would be actually twice the intensity, and the combined effect would be 83 decibels, because 3 decibels is a factor of 2 in intensity. So you can see that we're constrained to be less than 83 decibels. We can express a difference in intensity levels by using our logarithmic math. A difference would be intensity level 2 minus intensity level 1. And if I expand this out using logarithmic math, I would get 10 log I2 minus 10 log I naught minus 10 log I1 minus 10 log I naught. A minus minus in this second parentheses will be a plus, so my 10 log I naughts will cancel out. And this difference would be 10 log intensity 2 minus 10 log intensity 1, which in logarithmic math is 10 log I2 divided by I1. So a difference in intensity level is 10 times the log of intensity level 2 over intensity 2 over intensity 1. This might come into play if you had one point source of sound and you were going to be at two different locations, R1 and say R2. What is the difference in intensity level between those two locations? Well, we just showed that the change in intensity level is 10 log I2 over I1. If we were at two locations from the same power source of sound, at location R2, our intensity would be the power divided by 4 pi R2 squared from lecture number 1 in this chapter. And then at location radius R1, it would be the same power source over 4 pi R1 squared. The powers cancel out. 1 over 4 pi's cancel out. And we rearrange this as being the 10 log R1 divided by R2 squared. I'm going to decrement the power, bring that out front, so bring the 2 down. And I have that my change in intensity level between two locations, R1 and R2 from the same source, is 20 times the log of R1 over R2. So that could be a somewhat useful formula if we were trying to compare 2 points from the same sound source. Let's try one more example. The intensity level of an orchestra is 85 decibels. A single violin achieves a level of 70 decibels. How does the intensity of the sound of the full orchestra compare with that of the violin sound? Well, we can convert back for the full orchestra and would say that the intensity of at 85 decibels is 10 to the 85 minus 120 over 10. That's going to be 10 to the minus 3.5 watts per meter squared. Now if I look at the intensity of the violin, single violin, at 70 decibels, that's going to be 10 to the 70 minus 120 over 10, or 10 to the minus 5 watts per meter squared. If I took the ratio of these, the full orchestra to the one violin, the intensity of the orchestra to the violin will be 10 to the minus 3.5 over 10 to the minus 5, which will give me 10 to the 1.5 power, which is 31.6. So the intensity of the full orchestra to the intensity of one instrument, one violin, is 31.6. If we treated all the instruments as being almost approximately equal in intensity, then I probably have about 31.6 instruments in the orchestra. Here's a possibility of how we could solve this using the quote-unquote shortcut method. If I think of the orchestra as being the intensity of the violin, the intensity level of the violin, 70 decibels, plus 3 decibels, plus 3, plus 3, plus 3, plus 3, adding up to 85 decibels. So I have to have 3 5 times. That would correspond to the intensity of the violin times 2, times 2, times 2, times 2, times 2, 5 times for that. 2 to the 5th is 32. So the intensity of the orchestra is 32 times the intensity of the violin. That's a shortcut method, and it's basically saying that I have 32 instruments in the orchestra, 32 times the intensity of one single instrument. And that's the way it would work. The other way is more exact, but this way is quicker if you had to make a calculation quickly. So try your hand at some of these intensity problems and decibel problems. And our next thing to look at is Doppler shift.